That is about roadmaps. Okay, let's first introduce what is a roadmap, or what we call a roadmap in the sense of motion planning, and then we will see three kinds of roadmaps, okay, and the algorithms that we use to building them. Okay, roadmap, as its name indicates, no, it's a map. Well, it's a map that contains roads, a map that contains roads, and this is the main analogy that we have. No, you are from an era that when you want to go to some place, you just use the GPS. But when I was a kid and my parents want to drive far from home and they don't know the exact road, they take a road map and check which roads they have to follow, and they try to do the path planning till from the city that we live to the city that we want to go. No. Then this is the analogy that we want to use, but in a more mathematical speaking, for us a roadmap will be a graph. Now we will see how we define a graph, mathematically speaking, that basically connects, here are cities, for us will be configurations, positions in which our robot may be. These positions has to belong, or this configuration, sorry, has to belong to C space and are configurations that are feasible for our robot, and also they have to be inside C-free. I mean, they cannot be positions, configurations, sorry, that are in collision with obstacles. They have to be inside C-free. And the roads, for us, will be not roads, they will be paths, and these paths basically connect these different configurations, and also, if we discretize the whole path, then we will see the whole path belongs to C space, and they are available configurations for our robot, and all of them are in C-free. Okay, this is what a roadmap is for us. Then, as I told you, roadmaps are defined using a graph. Then I don't know if you know how to define a graph, mathematically speaking. A graph is a tuple, okay, that contains a list of vertices and a list of edges, okay? Sometimes instead of vertices, you may listen nodes. It's also standard, okay? Vertices or nodes, as I told you, for us will be configurations from our robot. Remember, configuration can be an XY position, but it can be an XY, theta, roll, pitch, yaw, Z, whatever position. Or it can be if we are dealing with manipulators, it can be the different configurations for the different values, sorry, for each joint in our manipulator. Everything is, anything of these are a configuration, valid configuration. And then the edges basically connect two vertices. An edge is something that connects vertex 1 with vertex 2 or vertex 20, whatever. Okay? Then some characteristics that graphs may have is that they can be directed or undirected. When we call that a graph is directed, is because there is only, I can go from this vertex to this other vertex, but I cannot go from this vertex to this other vertex. If I have only one direction, then it's a directed graph. If it's not a specific direction, then it's in an undirected graph, okay? Then graphs can be also cyclic or acyclic. When they are cyclic, it means that I can reach the same node, for instance, this node, coming from here, but I can create a loop from a node. No? Then if I start here, I then just can move. I don't know. Maybe it's too long. This one coming here, coming here, coming here, and then coming here. Then I've completed a full loop, a full cycle inside the same graph. It implies most of the time that I also have multiple paths. It means that for reaching, let me change color or just erase a little bit that. For reaching this specific node here, I can come from here, but I can come from here, but I can come also from here. Then I have multiple paths to reach the same vertex. And they are mostly used to model networks, okay? In our case, it will be networks of paths, available paths. There is a specific kind of graph that is also very popular in computer science that are trees, okay? Trees is a subgroup of graphs. Trees used to be directed, they used to be acyclic, and they are acyclic. They have always a single root and then multiple childs. They are a subgroup of graphs, okay? Graphs used to be more general. Then, coming back to our roadmaps and to path planning, as I told you, we will define these roadmaps using a graph, as we have said before, and inside this graph we will have the nodes or the vertices there. I will change a little bit from one to the other, sorry, that they correspond, as I already told, to collision-free configurations, that are these orange bullets that I put here, and then we will have the edges that are feasible collision-free paths, okay? Feasible collision-free paths. This is the only thing that's important for you to remember. Then, if we want to use a roadmap to do path planning, what we have to do is to ensure these three conditions. The first condition, first we need to define a start and a goal position. Here is the start position with this green triangle and the goal with this yellow star. Of course, these two configurations have to belong to free space, otherwise it makes no sense. And then what we need to check is these three conditions. The first condition is called accessibility. And accessibility means that I can connect my starting position to some of the nodes in the graph. Normally, we always check first the closest one. In this case, the closest one is this one. But I can connect it with with a feasible path. Okay, in this case, this is a feasible path. If I can do that, then it's accessible. It may happen that here I have an obstacle. I don't know. Imagine that here I have an obstacle. Then I cannot connect the goal, the starting position with the closest path, but I can connect it to this other path. Okay, then it's feasible also. Okay, but we need to check that at least we can connect the starting position with some of the nodes. We will normally start for the closest one because it's easy, but we can do that. The departability is exactly the same condition, but with the goal position, okay? That it means that we can connect the goal position with some of the nodes, with some of the vertices of our graph. Here, look that when I try to connect, I always use a straight line. I will talk a little bit about that later when we talk about local planners and global planners. But for now, when I try to connect things, I always try to use the straight line. We will improve on that later. Okay, then the departability is exactly the same idea. Okay, if I'm able to connect the goal with the closest, or even if the closest is not possible because here I have some obstacle, but I can connect it with this one, then it's fine. The condition of departability, it's okay. I pass this condition, and then I can plan on this roadmap. And the last part is now that, okay, let me just delete that. Now that we have selected this Q here, that we call it Q prima, and this Q here, that we call it Q prima prima, if we can connect these two nodes in the roadmaps can be discontinuous, okay? When I talk about the properties of a graph, sometimes graphs are unconnected. I mean, I can end up with two different graphs that they have no edge in common, and it's a single graph. This may happen with a graph, okay? Then this connectivity property here is not guaranteed. Okay, then we need to check that really there is really a path here. I marked this path with this red line because I think it's the shortest one that connects these two. But of course, we will follow this path if we have an optimal, well, it's not optimal, but I mean, if we have a good algorithm, maybe we just decide to go for another path and we just connect it using something like that. And it's also fine. The only thing that tell us is that they have to tell us this condition is that they have to be connected. How they are connected, how good is the path that connect them, it's not the condition in order to apply a roadmap for our algorithms. Okay, then the process is what I show you right now, okay? We will start building the roadmap. We will see later 3 different ways to build a roadmap, each one with their properties, with their advantages and disadvantages. But basically building the roadmaps is creating these nodes that are in the middle of C-free space, and then connecting them using, for now, straight lines. Okay, this local planner, that is the simple one that you can imagine, that is just connecting it with straight lines. And then this is done, when we have this done, the nice thing of roadmap is that we can reuse this part. This part, as you can imagine, is heavy, computationally speaking. It takes time to build a new roadmap every time, but we can reuse it. As soon as when the environment do not changes, if the environment do not changes, we can reuse the roadmap. Whenever we have this roadmap built, then we can start doing queries. And doing queries will be that, setting up a goal position and a starting position. And then every time that we do a query, we need first to discover this Q' and Q'', that to select the two nodes in the graph that are closer or that are connected at least with the starting position and the goal position, and search for the roadmap, basically, that connects this Q' with this Q''. And that's all. When we have done that, we already have the solution. Okay, let's see then how these roadmaps can be built. Okay, we will visit three possibilities that are the visibility graph, the Voronoi diagrams, and the probabilistic roadmaps. Starting with the visibility graph. Okay, here the main idea, I will then go a little bit slower with the algorithms that we can use to build them. But the idea is to use, if we have an environment that is defined using polygons, is to use the vertices of these polygons to trace lines. Okay, you see, to trace all these lines, they always go to the vertices of the algorithms. Okay, all these lines. What this will create is this roadmap that you have here, in which nodes always will correspond to a vertex or the starting or goal position. Okay, and then they have some advantage that they lead to paths that are optimal with respect to the Euclidean distance. But okay, for now, we cannot here compute some other factors. Okay, then for us will be optimal. Okay, but again, they have some problems that they pass very close to obstacles. As we put the vertices, the nodes in the vertices of the polygons, we are always almost touching all the polygons that maybe it's not what we want. Another kind of diagrams that we are going to explore a little bit are the Voronoi diagrams. Okay, these are like the opposite of the visibility graphs because they build roadmaps in which the paths pass to the farthest possible of any obstacle. Then these paths are not optimal at all, but they ensure that we are very far from obstacles. So they ensure clearance. I don't know if you know this word. Okay, clearance is that we move very far from any possible collision. Then for some applications, they are very useful because of that, okay? Because they give us the most safe first path, even that the path is not the best one. It's not the optimal, at least using Euclidean distance. And finally, we will see the probabilistic roadmaps, okay? We will do a full topic on probabilistic methods, and then we will explore a little bit more the probabilistic roadmaps because it's a huge topic. Probabilistic roadmaps, they are super used. They have a lot of utilities, probabilistic roadmaps. But here we will just introduce them. And here the nice thing is that probabilistic roadmaps, as the names indicate, are built a little bit just randomly. Okay, just we set up the vertices, the nodes in these roadmaps randomly, but we try to cover the full area and then to connect how we can these nodes. And with that, we can get paths that, although they are not optimal, they are close to optimal. We will see some properties later, and they are very fast to be computed. Okay, then it's a good alternative. Okay, then let's start with the first one, with the visibility graphs. I already explained you the basics of visibility graph. First of all, our environment has to be known. Remember that during this first semester, most of the time we will assume that the environment is known. And we need to define the obstacles in the environment. I told you the first day that we can define the environments in a lot of different ways. last week when we were talking about potential functions, and also when we were talking about back algorithms, we assume that our environment is a kind of grid map in which we have cells, and each cell can be free or can be occupied. This is a way to define the environment. Another way is just to define polygons. Okay, it's a pretty simple way also, and you know that you cannot be inside the polygon; you can be only outside of the polygons. Then here in the visibility graph, we assume that we have polygons. Of course, you can move from one representation to another. I mean, I can discretize these polygons into cells. Okay, and generate like a bitmap of that, and having, okay, inside the polygons is occupied and outside the polygons is free. And if I have a map with just some cells, I can just try to draw polygons around the obstacles. And we will not enter here in the techniques to do that, but it's possible if you have a discretized representation or a grid map representation, or you have a polygon representation, to move from one to another. It's possible. For here, we are assuming that we have the environment as a set of polygons, plus we need the starting and the goal position. Okay, in the potential fields algorithm and also in the back algorithm, we only need the goal where we are moving at. Here we need not the goal but also the starting position. Okay, I think in all the algorithms that we will see here, or almost in all the algorithms we will see here, we need that. Okay, from where we start and where we want to go, because when we build this visibility graph, we need to introduce these two elements. Of course, we can first build the roadmap, assuming that we don't have that, neither that. Then here there will be plenty of roads that will disappear, and then checking the portability and the, sorry, I want to say the correct name, the accessibility and the portability conditions, checking these two conditions, then create these extra lines, these extra paths, okay? But at some point, we need to know that. Okay, then what we will do is to connect the nodes, basically, as we have said, all the, let me just mark them, all the vertices in our map, everything, these, all of them, etc., plus the starting and the goal position will be included as vertices in our graph. And then we need to check from this node here, can I reach this? Yes, okay, then I add it. Can I reach this one? No, then I don't add it. I just delete it. I can reach this one? Yes, then I add it. I can reach this one? Yes, then I add it. I can reach this one? No, then I don't add it. All the possibilities, okay? All of them. Therefore, there are different algorithms to do that. One is the one I was trying to do right now, that is brute force. I think brute force, the word almost says, no, it's basically starting from one vertex, check all the others, and see if I can connect it or not. Yeah, tell me. Is the algorithm. The algorithm tells us to use only the vertices. Only the vertices. Yeah, in fact, if you use only the vertices, you can ensure this condition here, that you will find the shortest path. Okay? And there is another thing that, imagine, let me just clean it a little bit. If I'm in this vertex here, and I to connect it with this vertex here, then I will add this edge. The edges of the polygons will be inside the list of available edges, at least connecting neighbor vertices, okay? Because always from one vertex to their neighbors, the edge is valid, for us will be valid, okay? As I told you, this algorithm pass super close. In fact, it passes on top of the edges of the polygons that for some tasks will not be very good. But as you know, we can always expand a little bit our obstacles. We can do lots of different tricks. The same way that we did in the grid map, that we expand the obstacles. We can also do it here and expand a little bit the polygons. And then the map that we use to planning or to find the visibility graph is not exactly the map that defines our obstacles, okay? But in the list of vertices, remember, we will have a graph, with a list of vertices and a list of edges. Then in the list of vertices, we will have only the vertices in the polygons plus the starting and goal position. And as I told you, we can do it with brute force, but brute force give us, do you know the complexity of, when we talk about complexity in algorithmics, we try to define not how much time it will take to execute this algorithm, because this depends on the computer that you are using, but how many, more or less, operations or iterations, more than operations, is how many iterations you have to do in your algorithm. And then we always try to set up that with respect to some very important element in the algorithm. In this case, for instance, the number of nodes, the number of vertices that we have in our roadmap. Okay, then if we use brute force, it's the people that know how to compute these things, that tell us that the complexity of the algorithm grows exponentially, but to the order of 3, okay, cubic. It means it's slow, okay? Normally, we don't want algorithms with this complexity. We want algorithms, if possible, that they are linear, not exponential, but if they have to be exponential, a lower exponential. There is another algorithm that I will try to explain you now, that it's called the rotational plane sweep. This algorithm is slightly better. It's not super better, as you can see. Instead of n times n times n is n times n times log n. Okay, but this small difference, this small log here, makes that when you do this n super high, it changes a lot. Okay, the order of magnitude of the time that you spend computing the algorithm is reduced a lot. Okay, first let's see the brute force algorithm. Okay, the goal is to draw lines of sight from the Q star to Q goal to all visible obstacle vertices. Okay, this is the main goal. Well, and not only from Q star to Q goal, between them also. Maybe it's not the best sentence, sorry. The idea here is E sub aj, this is a vertex, an edge, sorry. Okay, this is the edge that connects vertex I with vertex j. Then what we are going to do is we will try to move from vertex I to vertex j continuously, or at least we will discretize this path, and if all the points or all the configurations that appear in between of vertex I to vertex j, if all of them belong to the C-free, into the free space, then we will add this edge to our list of edges, okay? Here, the way to do that basically is we have this S moves from 0 to 1, okay? When S is 0, we have 1 minus 0, it's 1, bi, then we are just in position bi, plus S, that is 0 times bj, S, then we are at bi. When S is 1, we have 1 minus 1 is 0, then this is 0, we don't count it, plus 1 times bj, then we are at bj. When S is in the middle, 0.5, for instance, 0.5, then we are at a half distance between bi and bj. We are 0.5 times bi plus 0.5 times bj, and we are just in the middle. Okay, if you do that from 0 to 1 in a continuous way, or we discretize that very tiny steps, we are checking all the possible points. Just one thing, we are not just checking that all these points belong to C-free, because as I told you, we also use the edges of the obstacles, we use the vertices of the obstacles, then we use CL of C-free, and CL is the closure of the C-free that includes all free space plus the boundaries, okay? It's just this CL here that maybe it sounds a little bit strange, it's just this closure. Then let's do it, okay? Starting from start to goal, okay? From the starting position, I try to draw lines through all the other vertices. Of course, I cannot draw a line from here to here, because all this part will be inside the polygon, and this will be okay, it's in collision, then I cannot draw this. But I can start drawing lines. We do it first from a start to all the positions and from goal to all positions. This is also a trick that some people uses, that is include the boundaries of the environment, the 4 boundaries of the environment, or the 8, or how many boundaries you put it, as also as vertices, okay? And then we try to do that, and then once we have done that from the start and the goal position, we do it for every vertex to every obstacle, from every obstacle, okay? Then we start here. This is a brute force algorithm. I start here and I do exactly the same. I check for all the algorithms. See that here I've added this line and this line, okay? Although they belong to the polygon itself, I add it in the graph, okay? Then when I'm done with this vertex, I move to this other vertex and I add more lines and more lines and more lines and more lines until, I think, no, here it's still to this vertex here, until we have done and we have completed for all possible vertices. And this is a roadmap, okay? Maybe it's not the kind of roadmap you are more used to see, but this is the roadmap. And because we have already included the starting and the goal configurations in the roadmap, we can directly found here a path that moves from a start to goal. Finding the best path from a start to goal is next lesson, okay? It's graph-based search. Searching paths in a graph. Today it's building the graphs, okay? It's we have split it in 2 lessons, but the idea is that, as you can see here, I can find, I don't know which is the best one, probably will be something like moving to here, then moving to here, then following this edge, and then moving to here. Probably this is the best path I can use to move from a start to goal. And if it's really the best path, I don't know, I'll just make it. But if it is the best path, this is the shortest one in using Euclidean distance. Then in terms of Euclidean distance, is the optimal one. Okay? The only problem of this method is that it is slow. Okay, as you can see, computing that is not slow. Okay, there are some exercises that we can try to do. Imagine that 0 here is the starting position, okay, start. The 5 is the goal position. And then what we want to do is connect, here I think I've not used the borders of the boundaries in this, but what we can do is just try to connect, from here I see vertex 3, well I don't see vertex 1, because to see vertex 1 I have to cross the obstacle. I see vertex 2, I see vertex 3, I cannot see vertex 4, because again I have to cross the obstacle, and I don't see vertex 5 for very little, but I don't see it. Then from vertex 1 I see vertex 2, I see vertex 3 no, but I see vertex 4, and I see vertex or goal point node 5. From the 3 I see the 2, I see the 4, and of course I see the star, but I don't have to check the previous ones, okay? The previous ones, if I use indirected vertices, they are already there. From 3, I see 1 and 2, and I see 4, and that's all. Then this is the kind of graph I will obtain. If here I have to find the best path, sorry, no, I forget 1. From 2, I see also 5. Of course, I forget this one. Then from 4, yeah, you are right. I think I skip vertex 2, Yeah, sure, I skip vertex 2. Yeah, from 1 I see yes, and from 2 I see 5 and 4. Yeah, sure. Now, then from here, if I have to find the best solution, probably will be moving from 0 to 2 and from 2 to 5, something like that. Okay, it's pretty simple if you don't forget things like me, okay? But if you just have to move slowly and do it, you can try to do the other one. You have the solution here, but I mean, it's something easy for you, okay, to do, and at least you should be able to do that. You understand the way. Just go step by step with calm. Don't forget any edge. Go in order, and it should be easy to do. Okay. Then let's try to present this a little bit better algorithm, the rotational plane sweep algorithm. This algorithm does almost the same And you will see that it takes, you have to do more steps in each iteration, but you have to do less iterations. And this, although for a small, for very simple environments, can cause you that it can be even worse in time or in CPU time. If we grow a lot our environment and we have lots of nodes, then the final complexity is much lower, okay? And you can find the paper here, and as you can see, it's not a very new paper, okay? It's pretty old. As I told you, all these algorithms that we will be talking, especially till next week, algorithms from next week are very useful nowadays, A*, Dijkstra, but Dijkstra I think is from the 50s. I mean, they are super old algorithms, but they are the basis. You need to know them. You cannot do a master in robotics and do not know the Dijkstra algorithm, okay, or the A* algorithms or any of these ones. But I mean, all these algorithms that we are going to see in this class are pretty old, but I think it's good for you to see. Here, if I'm correct, yeah, it should be a link and you can go to the paper. Let's see, the main idea of this algorithm is, I put here 7 steps, okay, is choose a vertex, then sort all the other vertices, sorting using the angle, we will see how it's done. Then we have what we call the active set, that is this S. We will first initialize this active set. I will show you then later how this is done. And then we are rotating, is what it's called rotational plane sweep, because we rotate following this order, so sort all orders, and basically we are like creating an edge that rotates. However, we don't have for all the vertices to see if the connection it's there or not. I've not explained that, but in the other algorithm, the complexity n to the cubic n, is because for all the vertices, you need to move through all the vertices, then this is the first n, and then you need to check all the other vertices, the second n, and then for checking that, you need to move, follow all the line and check that everything it's fine, and then it means that you are not intersecting any of the edges. That is the third n, okay? Here, the third n, it's a little bit reduced because we have this visibility set. And just using this visibility set, sometimes we will have to check it, if this visibility or not, but most of the times just keeping this set, just checking the set, that is something that can be done not in order n, but in order 1. We are going to see if there is visibility or there is no visibility. And then if there is visibility, we just add this edge. If not, we don't add it and we repeat the full algorithm. Okay. I tried to put here, I think this is the algorithm that you can find more or less in the textbook in which this algorithm appears. And also in the paper, okay. The idea is this one. We start with a set of polygons, the obstacles that we have, and the vertices. Well, we can extract from these polygons all the vertices, but the vertices are already there. What is empty is the edges. Okay, we don't know how many edges we will have there, and then the starting vertex. Okay, then this algorithm, this piece of this function that I put you here, is repeated for each vertex. Okay, the same way that in the brute force we start with one vertex, check all of them, move to another vertex, check all of them. Here we have to do it. Then this n, this factor n, it's exactly the same. The output will be a subset of vertices and in which you have line of sight, okay? Because you start from vertex B and the output is Bi, then basically you can imagine the output is not a subset of vertices, but a subset of edges, okay? It's edges that you have to add to your visibility graph. Then for each vertex, you need to compute this alpha I, that is this angle from the horizontal vector. Maybe we can go through the algorithm, but probably it's better if I just go through the example, because otherwise it can be a little bit complex. This, as I told you, this is the main algorithm that you can find in the textbook, but in the textbook there is always that says if visible, and this if visible sometimes is just slightly explained, but I try to do my best to put it not in words, but to put it in code. check it carefully, okay? This is my implementation. It can be some error here. I implemented and the Python was working, but then when you move from Python to pseudocode, sometimes you commit mistakes, at least me. Okay, then check it, and if there is an issue here, just tell me and we move through it all together. Okay, let's try to do a very, very simple example. Okay, imagine that we have this setup. We have a very, very simple environment in which we have only this obstacle here, that it's a triangle with 3 vertices, vertices 1, 2, and 3. Of course, triangle has 3 edges, edges 1, 2, and 3. And then we have also a starting position or node and a goal node. Okay, the first thing that we need to do, according to the algorithm, is sort all the nodes, then sorting from B1, B2, B3, B4, Bs. Of course, here I put already the names, the numbers, sorted, but why this is B1 and this is not B3 and this is B1 and this is B2, I don't know. Okay, then how we sort that? The idea is, starting from the node that we want to check the visibility, now we are only checking visibility from BS, not for the whole environment, only from BS, okay? Because otherwise it will be very long to do. Then we just create a straight line and a horizontal line, sorry. Okay, this line is horizontal. It's not moving from BS to BGO or something. No, it's just a horizontal line, okay? And then now imagine that I rotate this line like this. The first vertex I will sweep is B1, is this one, okay? Then this is B1. The second this line will touch will be B2. Then the line will continue here, and at some point it will pass through B3. Then this is the third one. And the last one I want to sweep is B4, okay? Then this is the sweep, rotational plane sweep. Then this is the sweep I want to do. Always starting with a horizontal line, okay? This is how I set up the order. Then the second thing I have to do is to initialize S. How we initialize S? Then using exactly the same line, this continuous red line that you have here, I need to check which is the edges I'm crossing. Okay, and here I see that I cross H1 first and H2 second, but I never cross E1 and E2, but I never cross E3. Then in my initialize, when I initialize this set, I put E1 and E2 with this particular order, okay? Here I have to check, I have to go through all the edges in order to initialize this set, then this is not very efficient. But from now on, instead of having to do the same for each vertex I want to check if I'm colliding or not, instead of going through all the edges, I will just update this set, and this is what will make this algorithm slightly more efficient. Okay, then now I will move to the B1, okay, then I will move the strip to B1, and then if now we will come back to the algorithm, okay, for each alpha 1, in this case is when I move the sweep in order to cross from BS to B1, then this is specific angle, okay, this is specific alpha, I will say if this new vertex that I'm now crossing, in my case B1, belongs to an edge E that is not in the set, I insert it to the set. And if it belongs to an edge E that is already in the set, I delete it from the set. Then if I come back here, what happens here? B1 belongs to these two edges, E2 and E3. E2 was already in the set. Then I remove it from the set. Remember, I used to have E1 and E2, now I remove E2, but it belongs also to E3. Then I add E3 in the set. Then my new set is E1, E3, okay? This is a small trick that it's not very clear when you read the algorithm, but it's super important that when you have done these two steps, adding and removing, you maintain S sorted by intersections distance from B along the current ray, okay? You need to keep this order, otherwise the algorithm is not working, okay? And doing that sometimes is a little bit tricky. Okay, whenever I have done that, I can just directly check the visibility. And if the visibility is okay, I add the edge. If the visibility is false, I don't add the edge. How we check the visibility? Okay, this is this algorithm that I prepared here for you. There are several steps. Yeah, sure.
In the previous slide, what's the line is sorted by intersection?
Create which one?
In the is sorted by intersection distance.
The third one, yeah. The S intersection distance from B along the current ray. Okay, then here imagine that along the current way, then the current way is this one. At which distance I intersect E1, and at which distance I intersect E3. Okay, E1 will be intersected at this distance, E3 will be intersected at this distance. Then I have to keep this order. Okay, the closer first. It's that. Okay. Of course, computing that is easy than computing the intersection with lots of edges, because here we only have to check for the ones that are in the set. Okay, then this reduces a lot than if I have to check it for all possible edges. But it has to be done. If you forget this tiny step, nothing works. Yeah, please interrupt me every time that there is some question. Then let's see now how we check the visibility now that we have this set. There are some things that are pretty simple. For instance, if B and BI belong to the same H, it means they are, imagine that we have this polygon here, and here I have BS, and here I have BI. Then I have an H, okay, that both elements are in the same edge. If this happens, of course, the visibility is true. We are always visibility with something that is in our same edge. Then we just return true. If they belong to the same polygon, then it's more tricky because, okay, a triangle doesn't work for me, but imagine that I have something like that. Here it may happen that they are in non-consecutive vertices, but still they have visibility. Okay, there is visibility here, or that they are in non-consecutive vertices. For instance, this one, let me move that. Well, I removed too much. I do something like that. Okay, they are in non-consecutive edges, but I don't have visibility, no, because I have to cross inside the vertex. Then this is a tricky part. Okay, then when they belong to the same polygon, then if there is a portion of the segment that connect them that it lies inside the polygon, then I have no visibility. If no portion lies inside the polygon, then I return visibility. This is a little bit tricky to implement. Okay, but you have to do it, otherwise it's not going to work. And probably is the condition that I put it in second position, and probably it should be put later because it's the one that takes more time to compute. Okay, then if the set S is empty, now when we are doing the algorithm, you will see that at some point the set becomes empty. Then directly you have visibility. You don't have to check anything. It's true. And then if assuming that E star is the first H in S that does not contain B or BI. Okay, remember we have this set S here, then in this case we have BS and B1, then we want to check which is the first H that do not contain BS, neither B1. For instance, E1 contains B2 and B3. Then, in this case, is this one. It's easy. But maybe imagine that the order was the opposite because E3 already contains B1. We are not using this one. We are using the other. Okay? Then, assuming that this E is the first edge in S, then we only need to check not all the edges in the wall, only the edges in the set S that do not contain B or BI. If E exists and it may happen that there are no one there is no H in S that do not contain either B or BI. It may happen then, but if it exists, if there is one and the segment B to BI intersects it, then we return false, otherwise we return true for the visibility. Okay? Then now that we know the whole algorithm, let's continue the steps. We have seen that computing the new set This is the new set that we have because E3 was not in the previous one and E2 was there and we need to remove it. Then we don't belong to the same polygon, then not the same edge, neither the same polygon. S is not empty, then we need to reach the last one, then is E1. Then we need to check only if BS, if this ray crosses this edge. Check that we only need to check one collision, not n collisions, only one collision. Yeah, it collides. Then because it collides, we don't add this edge to our visibility graph, okay? It seems that we have to do a lot of things before checking that, no? And it will be much simple in this algorithm just to check if we collide with this, or with this one, and that's all. But when you have thousands of edges, although you have to do some extra work to keep this set, having to check only one or two edge collisions is much faster than having to check all of them, okay? This is the main idea that I want you to transmit. Then, next step, we move and we were here, now we are here, okay? To this other alpha. Then, we need to remove from S the H3 and H1 because B2 belongs to H3 and E1. Then we remove it and now S is free, is empty, sorry, because S is empty, directly we can just say that this edge is visible, and that's all, okay? Then we will add this edge. Then we move to B3, that is the next one, and now we have B3 belongs to E1 and E2, then we add E1 and E2, and we need to check again the visibility condition. The visibility conditions, because BS and B3 do not belong to the same polygon, then they are not the same edge, they are not in the same polygon. S is not empty, then we need to check which is the first edge in S that do not contain neither BS and B3. None, E1 and E2, none of them contains BS, but both of them contain B3, then there is no one that do not contains B3, then the visibility is 2. And we add it. And finally, we have this final edge, that is this one here, before. We need to remove all the edges that contain before and BS. None of them, both E1 and E2 keep in the edge. Then we need to sort them. We have already sorted before, then it's fine. We need to check if they are in the same polygon. No, then they do not belong to the same edge. They do not belong to the same polygon. S is not empty. Just let's check which is the first edge here that do not contain neither BS and neither before. It's the first one, is E1. Then I only need to check if this and this collide. Yeah, they collide. Then it's false. I don't have to add the BS to before edge in my visibility. You see, although I have to do lots of extra steps, in the end, when I really need to check collisions between edges, it's pretty straightforward because normally I have only to compute one. And sometimes even not one. Okay, then this reduces a lot the complexity in my algorithm. Okay, let's do a break here, and then we continue with the Voronoi and the progressive roadmaps. Thank you. Okay, let's continue then with another kind of roadmap that we can build for our applications that are called the Voronoi diagrams. If I told you that the rotational applying sweep was an old algorithm, see that we are going down. Now it's 1975. Okay, Voronoi diagrams are a completely different way to create a graph, okay? To do that, we need to define several elements. For one side, we need the sites, okay, that are the points, these points. These sites can be points or can be a full obstacle, okay? It can be a full polygon, for instance, or something like that. It can be also a site. And then what we want to do is create regions around these points, these sites, that are at closer to this cell, okay, all this region here is closer to the black point in the middle than any other point, than to any other side, okay? Then this point, it's closer to this than to this, to this, to this, or to this, to any of the others, okay? This is the main idea. All the regions we call them cells. And where the cells, the limit between two cells are the edges, okay? Therefore, the vertices appears, now in the other algorithm, in the visibility graph, the vertices was the simplest thing to found, no? Because are just the vertices in the polygons plus the goal position and a start position. Here, no. Here, the vertices appear in the intersection of three or more of these edges that appear from the boundaries between two cells, okay, or two or more cells in this case. Okay, then this is completely different the way in which we build these Voronoi diagrams. But the best thing of these diagrams is that they maximize the clearance between the robot and the obstacles. Okay, then if we want to follow a very safe path, following the edges that the Voronoi diagram describes, it's a very good option. Again, here we are only creating the roadmap. We are not explaining which vertex, which edge or which vertex, which edge we need to follow in order to reach a particular place. Only how we build these edges. Then this is a little bit the steps that we need to follow in order to build these roadmaps using a Voronoi diagram. First one is obtain the sites. As I told you, sites can be single point, this is the simplest case ever, but it can be a full polygon, for instance, that will be our obstacle. Then, to build the Voronoi diagram, one possibility, or at least the simplest solution, it's, again, we discretize our wall into cells, and for each cell, we say, okay, which is the distance between this cell and any of the sites that we have defined. Sites can be points or can be polygons, then which is the closest polygon to this point here, to this cell here. Okay, is this one? Then I put here, if this polygon 1, then I put number 1. If it's polygon 3, I put number 3. Just the index of the polygon, the obstacle, the site, whatever you want to call it, that is closer to it. And with that, you will like paint your environment with labels. Okay, and each label will represent the point that is the polygon or the site that is closer to this specific cell. Whenever you have done that, you only need to check for the boundaries. And in the boundaries, when you change from all these cells here are closer to polygon 3, and all these cells here are closer to polygon 4, then the boundary between these two groups of cells, this will be an edge. Then you just draw these edges, and you will obtain automatically the edges in your roadmap. And when these edges, there are 3 or more edges that are coincident in a point, then you will have an edge there. A node there or a vertex there. Okay, this will be how we extract the roadmap. This is the same I try to explain you in plain words, but in an algorithmic way. Then here we set the obstacles, a grid, and the boundaries of this grid. And the output will be, again, another grid that will contain here, basically will be for this part, for the step 2, how to construct the Voronoi diagram, not how to extract the roadmap, okay? This is something that I will not include here in the algorithm, okay? Basically, we move through all the cells for A and J in the grid. Here, sorry, I use a square grid. Maybe it will be easier if I put here 2 different values, and then here you will have 2 different values, but this is just moving through our environment. I mean, it's quite simple. We compute for each position, we compute the position of this particular cell, like in Euclidean, no? Because remember, we will see that later, that we always have this duality in I'm in cell 3,3, but cell 3,3 represents which distance with respect to the origin. Okay, then in order to compute the exact position with respect to the origin, sometimes we need to change from cells to wall coordinates or from wall coordinates to cells. Okay, this is something that we will be doing a lot next semester, because we will keep working with cells to store where are our obstacles, where is our free space. But vehicle, it's not in cells. When we look to when you with Professor Ridao, you compute localization, you don't know I'm in cell 416. you know, I mean, this X and in this Y, then we always need to transform from wall coordinates to cell coordinates or grid coordinates. Okay, then this is basically what we do. And then when we know the position of the robot instead of in cell, the position of this particular cell in wall coordinate, then we just compute the distance with all the obstacles and we get the one that is closer. And then we don't want the distance itself. I don't care if I'm closer to this obstacle 3 meters and to the other 5 meters. I just want the ID, is why I say here obstacle ID. I just want the ID of the obstacle that is closer to me. Okay, and then what we do in this Voronoi diagram is we assign to this position, or to this cell, the ID of the obstacle that is closer. Okay, if we apply that, imagine that we have the same environment that we have before, and now I assume that this is one obstacle, all of this is one obstacle, all of this is another obstacle, and all of this is another obstacle. Then I need to discretize my cells, my environment in cells. Imagine that I'm discretizing this in cells. I will not do it for all, of course, but something like that. And then for each cell, first I need to compute the distance. If this is the if it's the wall origin, if this is the wall origin, then I need to compute the distance of this cell, that maybe is cell 0, 0 or whatever, depending if you use NumPy or whatever. Sometimes cells do not start to the 0, 0 of your wall. Then I need to compute the position of this cell in the wall, and then the closest distance from this cell to this obstacle, probably this, the closest distance, the distance of this cell to this obstacle, and the distance of this cell and this obstacle. I don't know which is the closest one. Of course, if you use sites are single points, this is super easy. It's just the Euclidean distance. It's square root. I mean, it's trivial. If you use a polygon like I'm using here, okay, it's not so easy. Okay, you need to compute probably the position, the distance to any vertex, or you need to use some trick, but sometimes it's not in one of the vertices, the closest point is in the edge. Then, okay, you need to compute that. Whenever you have done that, you just assign here the level of the closest obstacle, the level of the closest obstacle, etc., etc., etc. If we do that for all this map, we end up with something like that. Okay. Here, I have to explain that. I've added, like here, imagine that here I have another obstacle, that this is another obstacle, that this is another obstacle, that this is another obstacle, this is another obstacle, and this is another obstacle. In this way, I don't have only 3 sides or 3 obstacles in my environment, I have 7, okay? And then for each region, okay, then all this region here, the closest obstacle they have is this one, this edge here, the top edge. However, for all the points here, the closest obstacle is this one, okay? And this is a very simple implementation. You see, I even check the cells inside the obstacle itself. Of course, the distance of these points with respect to this obstacle are 0, and therefore it's the closest obstacle. But this is just obtaining the Voronoi diagram. Now we want to extract a roadmap from here. Then there is another step that is say, okay, then my graph, my roadmap, should be something like that, where I have a node here, I have a node here, I have a node here. Look that here edges are not even straight lines. Doesn't matter, You can have edges that are not in a graph, of course, but here we have it, okay? This is a Voronoi diagram. Then specifying that is not so simple than it was, I'm missing this one. But this is the graph that we have extracted. Of course, if we need to transform that in a real graph in which we can do just straight lines, then it's a little bit more complex. But you can add in your graph that you have your graph. It's a vertex and an edge. Nobody tells you that this edge has to be defined, this H has to be defined as BI, BJ. You can define that as a list of points. Okay, an H can be a list of points that connects BI with BJ. It's true, but that explains you exactly how you have to pass the path that you have to follow to reach BI from BJ or BJ from BI, whatever. Okay, then you can still use a graph. The only thing is that the representation of this graph will be slightly different. Okay. Of course, this is a brute force to create a Voronoi diagram. There are other methods that are a little bit better, but I'm not going to enter on that. And now let's move to the last, okay, no. And then let's going to move to the last family of roadmaps that probably are the ones that we are going to use the more. That are the probabilistic roadmaps. Why we want to use something probabilistic? Okay, the things that are explicitly geometric, that they never change. If I compute the visibility graph for an environment, I will obtain always the same result. If I compute the probabilistic roadmap, because it's a little bit random, the way in which I generate this, very random, the way in which I generate it, sometimes I can obtain a super nice roadmap, sometimes I can obtain a roadmap that is not very useful. Then, why we want that? We want something that is probabilistic instead of something that is explicit. Because when we start increasing the dimensions, when we're working with 2D point robots that are only X, Y, things like that, everything is easy, we can use explicit representation. But when we increase our dimensionality, we use drones that move in the 3D space with X, Y, Z, road PGO, or arms that have lots of degrees of freedom, etc., it becomes impractical. Okay, these explicit representations becomes impractical. And also compute exact solutions sometimes is exponential on the number of dimensions. Then it's not feasible to do it. However, if we just sample, we build a roadmap that probably is not perfect, but that have some elements that make them feasible, that make them a very nice solution, and you will see a lot of properties that we will see right now that keep sampling and sampling and sampling, we can reach something that is almost optimal and things like that. Okay? Is why, basically it's because of that, because they are efficient in high dimensions. Efficient in high dimensions. This is the most critical thing, that although right now we are assuming a very low dimensionality problem, you have to think in the future, and in the future you will work with real robots, and real robots are not points. Okay, they have lots of dimensions. Then the key idea of that sampling-based approach. Okay, just sampling positions, sampling vertices, and then using a local planner to connect them. Okay, I think I was checking now during the break if I have an explicit slide explaining the difference between the local planner and the global planner. Sorry, I don't found it. Then I forget to add it. In my head it was there, but it seems that it's not there. When we talk about a global planner, we mean that we want to reach from some position, starting position, a goal position, and then there is no direct route to go from here to here. Okay, I cannot go directly from here to here without colliding with an obstacle. Then I need to transform this path into something more complex, like the blue one that I've put you here. And although this is quite simple to use, this probably a nice local planner will be able to solve that. But imagine a maze, in which it's not clear where you have to move. Then a global planner, it's something that plans in ahead, that normally has access to the environment and is able, using this privileged information that it has access to the environment, to find which is the best path. And normally it analyzes a lot of different paths and looks for the best one. This is what a global planner does. A local planner sometimes is implemented as a controller. Okay, and when I say a controller, it means, I don't know if you have done this lab. Yeah, I think you have already delivered. It was fine. Someone yesterday told me that the deliverable date was wrong. I changed it. I think I hope all of you have been able to deliver your lab. But when you want to move to a point, you can just, for instance, if you are a differential drive or a bicycle or a Ackermann vehicle, you just control your steering and move forward towards it. Okay, if there is some error to the heading that you want to follow, then you just try to correct the error with the steering or with the angular speed, and then when you are more or less facing the goal, you just move straight and that's all, and you reach it. This is what a local planner normally does. Of course, there are local planners that are a little bit more clever, and if there are obstacles around, they are able to sort the obstacles. But they don't plan ahead. They don't plan, okay, if I pass through this side, it will be more optimal than if I move to the left. No, they just avoid the obstacle, okay? This is something that we will see in the second semester, for instance, dynamic windows approach or some other local planners that we will see. Okay, then what normally people does is to combine a global planner, some algorithm that has access to the environment and that is able to find a nice route from your position to the goal position with local planners. Something that it's more stupid if you want, but probably is reactive. It can avoid a dynamic obstacle that you have not foreseen in the global planner. Maybe they have global planners normally generate this kind of paths, straight lines. A robot cannot follow a straight line. Okay, a robot has to follow a path that is smooth. Okay, something more like that, more smooth. Then the local planner probably has better control of the dynamics of your robots and all these kind of things. Okay, then is why we normally do this difference between what is a local planner and what is a global planner. Right now, in this first semester, for us, a local planner is something that just is able to move from one point to another, for instance, from here to here, following in a straight line, and therefore it always connects these two edges, these two vertices. It can only follow this edge if there are no obstacles in the middle. It's pretty stupid local planner, okay? But for now, assume that for us, a local planner is, there is a line of sight from one to another, okay, then the local planner success. When instead of having a point, we have a vehicle, and maybe we have the vehicle pointing this direction, and we know that for the dynamics of the vehicle, in order to reach that, it has to follow this trajectory, then our local planner will tell us, no, the connection, this edge, is not possible, because if you have this orientation here and you want this orientation here, the only path I know how to do is this one, and this one crosses an obstacle, and then it's not correct. But for now, a local planner is just, there is line of sight, it works for us. Okay, then having said this some parentheses about local planner and global planners. The key features, as I told you, is that we randomly sample, and we sample only free space, or we sample randomly, but we check if the samples that we have random belong to free space or not, that is the same. And then we use this local planner to connect nearby samples, and for us, this local planner is just the line of sight. You can connect these two configurations with a line, it's fine. The local planner succeeds. If not, no. Okay, some nice properties that probabilistic roadmaps have. They are probabilistically complete and asymptotically optimal. Okay, we have seen what is a complete planner. Okay, if you remember, a complete planner is the planner that if there is a solution, it finds a solution. And it just tells you that, no, can I go from point A to point C? And if there is a solution, even if there is only one solution, it returns yes, you can go it. This is a complete planner. An optimal planner is the one that not only returns there is a solution or there is no solution, but it returns the best solution in accordance of some cost function, okay? For now, our cost function most of the time is Euclidean distance, the shortest path. Normally we use this cost function, but we can change this cost function to energy, to safety if we want to move far from the obstacles, plenty of other things, okay? But here, look that we don't have complete and optimal. We have probabilistically complete and asymptotically optimal. Then let's see in a little bit more detail all this notation about completeness and optimality. About completeness, as I already told you, complete means it always tells you, and this is something that I make note clear explicitly the first time I presented the term of complete, but it's important that it always terminates infinite time. Okay, it's not enough to tell me there is a solution or there is no solution, but this has to be done in infinite time. It seems logical, but it's an important distinction. Okay, if you have an algorithm that is very good, but it can be running forever until it found a solution, then it's not a complete planner. Okay, and it just says that report if the path is feasible or not, or if feasible path exists or not. Probabilistically complete planner, that is what we have said that roadmaps are a little bit different. If a solution exists, the probability that the planner finds it's close to 1 or it approaches 1 as much number of the more samples that you are, the more closer you are to this 1. It means that in infinite time, if you are able to generate an infinite number of samples, for sure, you will find the solution. But it's not guaranteed because you will not be doing infinite number of samples. Then, although the more samples that you add, the closer you are to get the real solution, if it's complete or not, until you don't add infinite number of solutions, you don't know that. This is not true for all the probabilistic roadmap algorithms. It's not true for all of them, but it's true for some of them, okay? We will see the difference when we do the other lesson about sampling algorithms in more detail. And then we have resolution complete planners. As I told you, most of the time we are working with environments that we discretize. Okay, imagine that we need to find a path from one point A to one point B, and there is a corridor that is very narrow, it's half-meter narrow, and for the way that we discretize our environment, this corridor disappears. No, it may happen. Then we will not find a solution, but not because there is no solution. It's because the resolution that we are using, there is no solution. Okay, then is that if a solution exists that can be represented at the chosen resolution, the planner guarantees to find it. However, it may happen that there are paths that require higher resolution and that we miss this path. Okay, this is about completeness. Let's talk now about optimality. This is almost the same. An optimal planner, as we have said, always find the path that is optimal with respect to some cost function. And as I told you, normally, right now we are using length, but we can imagine other cost functions like energy, for instance, is a popular one, especially in the more advanced algorithms like in reinforcement learning or things like that. You have a dog that has to walk from point A to point B. And of course, you want it to reach it the faster the possible, but maybe you are also more interested in preserving some energy or avoiding high impact movements or things like that, and then your cost function can be very complex, okay? And maybe you see that the trajectory is not the best one, the robot is maybe oscillating a little, doing a kind of sinusoidal trajectory, something like that, but it's the one that it's more smooth, that requires less energy, that takes less time maybe, etc., etc. Okay, then, but for now, length, okay? You can imagine that length is the one that we are going to use. Then the optimal planner, for now, tell us which is the shortest path. However, if we have an asymptotically optimal planner, that we have said that some probabilistic roadmaps are asymptotically optimal, not all of them, then it means that the cost of the solution returner, it's getting to optimal, it's improving when we add more samples. The same that we said before, okay? If we add more samples, we can be sure in the end, when we have had infinite number of samples, that the solution is complete. Then here, again, the more samples we add, the more optimal is our solution. This does not happen all the time. If we use a standard PRM or a standard RRT, that is a path planner algorithm that also uses sampling, they are not optimal. They are not asymptotical optimal. However, if we use the PRM star or the RRT star, we will see all these algorithms in more detail in another lesson, then yes, then the more samples we add, the more closer we are to the optimal solution. And if you are not optimal, then you are suboptimal. And suboptimal planner finds feasible path, if one exists, but the path can be not the optimal. Back algorithms, if you remember, back one was not complete, not optimal, then it's a suboptimal, or back two or back three that they were, back zero was not complete, back one and back two were complete, but they were not optimal at all, then they are suboptimal planners, okay? They give us a solution, but this is not the best solution ever. Okay, then now that we have introduced all these concepts, okay, local planner, global planner, asymptotically optimal, probabilistically complete, all this stuff, let's see how we create a roadmap. As I tell you, this is just an introduction because we will do a full lesson about sampling algorithms, and we will talk again about roadmaps, PRM, the probabilistic roadmap generation, but let's see here the generics, okay? Again, we define a probabilistic roadmap with a graph that contains vertices and edges. The new thing here is that in visibility graph, vertices belong to obstacle vertices or goal start positions. In the Voronoi, vertices were a little bit difficult to identify because they belong to where three edges coincide. Here, the vertices are randomly selected between collision-free configurations. It means they have to belong to C3, but are randomly selected. Okay? Then we create edges that connect these vertices, and they are collision-free paths, okay, between these edges. To do that, we are going to use a local planner, and the only thing that our local planner will do is, okay, imagine that I want to connect this vertex with this vertex here, then my local planner, what it will do is just create a straight line, discretize that, and check if for each one there is in collision or it's not in collision. If I try to do the same, but for this and this, I will just connect these two vertices, I will discretize this path, and because I notice that some of these points are in collision, then I will say, no, this path is not valid. Then right now my local planner will be that simple, okay? We need a distance metric, okay? We need to be able to measure distance between 2 points. If we have XY, it's super simple. If we have theta in the equation, okay, we have not only points, but we have orientation, that most of the robots has an orientation, then things can be a little bit more complex. And then the vertices can be sampled in a lot of different ways. For instance, here I don't see if you see a kind of pattern, but I've used a trick that it's not very good, in fact, to use this trick, but I just do it to make the graph a little bit nicer. That is, I don't allow, when I put a sample, imagine I put this sample here, then I do not allow the system to sample anything closer to these vertices. Then there is no other sample around it. The same for this one, I sample this one, then there is no other sample around it. If you use this kind of tricks, then you are messing with a lot of the nice properties of asymptotically optimal and these kind of things. Then normally it's not good to do this, but sometimes it's good. it's difficult to say, no? But for some applications, although you get rid of some of these very nice properties, it can be good for you because you have a super wide area, and what you don't want is to concentrate lots of samples in the same place. But if you do these things, then you lose some of the properties. Then is why you can, but we will study that. Different techniques to sample. Yeah, tell me.
Why not all the points are connected to all the possible points?
Yeah, this is another thing that we will see right now. Basically, this is a criteria that you choose. Normally, we choose how many points we want to connect each vertex, and then I think it's just in the next step. Yeah, I can explain you it here. Okay. Okay, this is how the properties that we have and how it looks. And to do it, then we just create this empty graph. In this empty graph, we randomly sample configuration. As I told you, we will see different ways to sample these configurations. But if you just stay for a uniform sampling, it's fine. It should be fine. Then we check that the samples that we have done are collision-free. Then we require some collision detection function. Normally, you will see in a lot of the implementations some function called isValid or something like that. Okay, and you just pass here a configuration, and this function returns or a boolean. Okay, true or false. Something this simple, you have to implement it normally in the second semester. You will have to implement lots of time this function for different environments, different representations, etc., etc. Then you repeat that until you have the n vertices. This is a way when we specify a roadmap. We can say, I want n vertices, and for each vertex, I want to connect it with the k closest neighbors. That is exactly what you were telling me. Normally, we don't connect everything with everything because it will take a lot of time. It's just to be fast, okay? Nice thing of probabilistic roadmaps is that it's fast to build them. If we have to connect all with all, we end up having the same issues that we have with the visibility roadmaps, that it's very expensive to connect everything with everything, and then we need to use some strange algorithm like the rotational plane sweep, etc., etc. Here it's when we create, and the most of the algorithms, what they do is when they are creating these configurations, they already sort them in a kind of KD tree or some structure like this one. Then it's super fast. Say, okay, tell me the 5 closest points to this configuration, to the 5 closest configuration to this configuration. Of course, here you need to specify a distance function, and it's what I tell you. If we are using XY, distance function is trivial, but the moment in which we start adding and messing with orientations, things get a little bit more complex, but we will see. But okay, the next steps, whenever we have these n vertices, is for each vertex, select its k closest neighbors according to one function, to one distance function that you need to define. And then using a local planner, again, the word local planner, as I told you, straight line, discretizing, no collisions, it's fine. Collision, no, it's not good. Then we attempt to connect. Okay? Here there are like different solutions. You can say, no, I want to connect my vertex always with k elements. What may happen is that you fail building the roadmap because you sample one configuration that is free, but it's just in the middle of obstacles, and then you cannot connect it, and then you fail to building your roadmap. Or you can say, no, I just take the k closest configurations and I try to connect it. If I succeed, I succeed. If I can connect only with one, with one. If I connect with zero, and I will have an isolated vertex there. Okay, this is normally how it works, but then you can end up with unconnected graphs. Okay, a graph that you have just a single big G with a list of vertices and a list of edges, but when you draw it, you see that in fact there are unconnected graphs. Okay, this may happen. And this is one of the things that we will see in the next lesson, and we will try to fix, at least to propose you ideas to fix it. Whenever we have done that, we use the local planner to attempt to connect it, and if the local planner is collision-free, we add the edge. That's all. Okay, this is, I think it's pretty simple. Here you have the same that I put in works again in pseudocode. I like to put the things twice, but I think some people see better, understand better things with text. Some people understand better the things with code. Again, if you found any mistake in the codes, these codes, I've done it, but I do it in Python. I translate it to pseudocode, and it can be errors. So just tell me. But I think it's quite simple. We just initialize the list of vertices and the list of edges. While the number of vertices is smaller than n, we just randomly select a new configuration and check if the configuration is free. If the configuration is free, we add it into the list of vertices. And then when we have the list of vertices, we use the k closest neighbors. As I told you, if we use a KD trees or things like that, I don't know if you are familiarized with these structures. it's fast, it's a fast process. And then for each one, we just try using a local planner to connect. If the connection is feasible, we add the edge. If not, we don't add the edge. And then let's see if our roadmap is connected or it is not connected. And this is the steps. We start from here, we have 10 nodes, and with connectivity K2, we try to connect all with all. Okay, here I think all have, the problem of connectivity 2 is that for this vertex, I ask it to connect it with 2. Then it connects with this one and with this one. But then the two closest vertices of this one, the two closest vertices of this one probably are, I don't know, this and this. Therefore, this one ends up not with 2 connections, end up with 3 connections. Okay, this may happen. It's natural. It's not a problem with that. And that's all. Okay, this is what I wanted to show you today.